For centuries, humanity gazed up at the stars, pondering the ultimate questions about our universe's origins, age, and fate. Were the heavens eternal, static, and unchanging? Or did the cosmos have a beginning, a moment when everything we see today burst into existence? This burning question captivated minds from ancient philosophers to modern scientists. But it was in the 20th century that we took a gigantic leap forward in solving this cosmic mystery, and at the very heart of this revolution stood Edwin Hubble. To understand Hubble's transformative role in the Big Bang theory, it's important to first set the stage. In the early 1900s, the prevailing view held that the universe consisted solely of the Milky Way galaxy, a solitary island of stars, adrift in infinite darkness. Telescopic images revealed hazy patches of light called nebulae, and their true nature was hotly debated. Some argued these were neighboring clouds of gas within our own galaxy. Others suspected they were island universes, vast collections of stars far beyond our cosmic home. Complicating matters, in 1917, Albert Einstein published his general theory of relativity, revolutionizing our understanding of gravity and the structure of space-time itself. Yet even Einstein hesitated to accept the full implications of his equations, which suggested the universe was dynamic, either expanding or contracting. To align with the prevailing belief in a static universe, he introduced the so-called cosmological constant, a fudge factor meant to keep the universe eternally balanced. Then, a critical breakthrough occurred. With the advancements of photographic plates and ever larger telescopes, astronomers acquired new tools to peer deeper into the night sky. At the Mount Wilson Observatory in California, the 100-inch Hooker telescope began its work, the most powerful in the world, and a window to cosmic revelation. Edwin Hubble entered this scene as a rising astronomer with a keen analytical mind. He set out to solve the riddle of the fuzzy nebulae. Using the Hooker telescope's extraordinary resolving power, he examined the famous Andromeda Nebula and others. Hubble searched for a special kind of variable star called a Cepheid, whose unique pulsation allowed for precise measurement of distance. When Hubble identified Cepheid variables within the Andromeda Nebula, the result was astonishing. These stars were so far away that Andromeda could not possibly reside inside the Milky Way. It was a separate galaxy, millions of light-years distant. This discovery, published in 1924, shattered the old cosmic order. The universe was vastly bigger than anyone had imagined, teeming with galaxies spread across immense, unimaginable gulfs of space. But Hubble's work had only just begun. The next question was even more profound. What was the ultimate shape and fate of this expanding cosmic realm? Astronomers had long noticed something curious when they analyzed the light from distant galaxies. When a light source moves away from us, its spectral lines shift toward the red end of the spectrum, a phenomenon called redshift, akin to the Doppler effect we experience with sound waves. In the 1910s, Vesto Slipher began accumulating evidence that most spiral nebulae exhibited significant redshifts, implying that they were moving away from our vantage point. But it remained unclear how these velocities fit into the greater cosmological picture. Edwin Hubble took on the task of compiling the distances and redshifts for dozens of galaxies, building on the foundational measurements of Slipher and others. Hubble's painstaking research culminated in a historic 1929 paper. Here, Hubble reported a simple, striking relationship. The farther away a galaxy was, the faster it appeared to be receding from us. This relationship became known as Hubble's law. Mathematically, Hubble's law is stated as V h0xd, where V stands for a galaxy's recessional velocity, h0 is Hubble's constant, the proportionality factor, and d represents the distance to the galaxy. This data-driven revelation was not merely a curiosity, it was the smoking gun that the universe is not static, but expanding, with every galaxy racing away from every other as the fabric of space itself stretches over time. This empirical foundation changed everything. If the universe is expanding today, simple reasoning suggests that, looking back in time, The cosmos must have emerged from a denser, smaller, and infinitely compressed state, a primal cosmic fireball. This insight forms the very heart of the Big Bang theory. The Belgian priest and physicist Georges Lemaitre had already intuited as much. In 1927, he formulated the idea that the universe began as a primeval atom and drew similar conclusions from general relativity. But it was Hubble's observational data, the methodical linking of distance with redshift, that provided the concrete, measurable evidence. The universe was not eternal and unchanging. It had a dynamic history, a beginning some finite time ago. Hubble's findings were initially met with a mix of excitement and skepticism. Questions lingered surrounding both the methods of measuring galactic distances and the interpretation of redshifts. Was space itself stretching, or were the galaxies moving through space? Had all matter really originated in a primordial explosion, as the term Big Bang, coined somewhat derisively by Fred Hoyle in 1949, implied? Regardless of doubts, Hubble's law was a turning point, setting the course for modern cosmology. Over time, improved observations would support and refine Hubble's conclusions. The measurement of the cosmic microwave background, the faint afterglow of the primordial fireball, provided dramatic evidence for the Big Bang. Elemental abundances, mapped out by nucleosynthesis theory, fit the predictions made by an evolving, cooling universe. The implications of Hubble's work extend far beyond historical curiosity. His discoveries upended our philosophical understanding of existence. The universe, it turns out, is not a timeless backdrop for cosmic drama. It is a story in progress, with a beginning, a now, and an unfolding future. Space itself is expanding, carrying galaxies along in its inexorable flow. Every moment we gaze into the depths of the universe, we literally peer backward in time, witnessing the remnants of creation itself. Yet Hubble's role in the Big Bang theory is not merely that of a detective unearthing clues. His research established new standards for precision, objectivity, and method in astrophysics. By seeking out unbiased ways to measure distances, using Cepheids and later refining with supernovae, and cross-referencing these against spectroscopic data, he brought scientific rigor to questions that had previously been matters of speculation or debate. Today, the rate of expansion Hubble measured, Hubble's constant, remains a vital parameter, but ongoing research has revealed its value to be subtly complex and still uncertain. Modern telescopes, using a suite of distance indicators and advanced imaging, keep refining this crucial number. Notably, some tension exists even now between measurements taken from the local universe, using supernovae and Cepheids in the tradition of Hubble, and cosmic background observations, hinting at new physics waiting to be discovered. Nevertheless, every new piece of evidence leads back to the foundational work of Hubble, whose insight revealed that the universe had a beginning and would have an ultimate fate. Hubble's influence also transcends technical achievement. It is cultural and existential. His discoveries altered the human story, moving us from the center of the cosmos to participants in an unfathomable, dynamic universe. The knowledge that everything, from the atoms in our bodies to the light from distant galaxies, shares a common origin in the Big Bang, connects us deeply to the universe's dramatic journey. To truly appreciate Hubble's role, imagine the chain reaction set off by his findings. Physicists, cosmologists, and philosophers were compelled to confront questions about the origin of space and time, about what, if anything, came before the Big Bang, and about the ultimate fate of all things. The expansion Hubble described implies a universe that will either go on stretching indefinitely or perhaps recollapse in the far future, depending on the ultimate balance of energy and matter. Each new discovery, dark matter, dark energy, inflation, the accelerating universe, builds on the foundation Hubble poured. Edwin Hubble himself remained scientifically cautious, often emphasizing uncertainties in measurement and interpretation. Yet his measured approach only underscores the seismic nature of what he had revealed. By transforming abstract, speculative questions into matters of empirical investigation, he turned the universe's history from myth into science. As we continue to map the cosmos with ever greater precision, from space telescopes that bear his name to instruments that can peer back nearly to the first moments after the Big Bang, Hubble's legacy endures. Every new revelation, every refinement in our understanding of cosmic origins stands as a testament to the power of observation, open-minded inquiry, and the unending human quest to know where we come from and where we are going. In the grand narrative of the cosmos, Hubble occupies a pivotal chapter, a moment when the universe, once thought static and eternal, was revealed to be dynamic, ancient, and unfolding. His discovery awakened us to the fact that we inhabit a universe with a story that began nearly 14 billion years ago with the Big Bang and continues to unfold in every star, every galaxy, and every one of us. The answers Hubble found are not endings, but beginnings, a revelation that the greatest journey in science is always, in some sense, just getting started.